Hello, everyone. It's my pleasure to welcome Satinder Singh, who is a professor of computer science and engineering at University of Michigan, and also the CTO and chief scientist of Cogitai. Before that, he was the chief scientist at Syntec, a principal research scientist at AT&T Bell Labs, an assistant professor at University of Colorado Boulder, and a postdoc at MIT's Brain and Cognitive Science Department. His research focuses on developing the theory and algorithms for building AI agents from interactions in complex environments. He's also the fellow of AAAI and has long-standing contributions in the area of reinforcement learning, multi-agent systems, etc. He also helped co-found the Reinforcement Learning and Decision-Making Meeting, which is a biennial meeting that brings together computer scientists, psychologists, neuroscientists, and various other folks. Today he's going to talk about intrinsic rewards and continual learning. So please welcome Satinder.
Thank you all. So feel free to interrupt me at any time. Let's make it completely informal. And so I'm just going to, I have a whole bunch of material to cover, but I'm totally happy to slow down as much as you want and make it as interactive as you want. So I'm going to talk primarily about intrinsic rewards, but in the context of a problem space that I call continual learning. So let me just situate continual learning in the field of learning and AI more broadly. So we know what supervised learning is. It works really well. You have fixed data sets. You have human-labeled data sets. You have fixed tasks. And we know how to do this. So lots of progress in AI has come about in this framework of supervised learning. Reinforcement learning, which is something an area I've been working in for a long time, has made a lot of progress too, but I would contrast that with supervised learning by saying it's human designed task, but self-collected data. So in supervised learning, the data set is fixed, the task is fixed. In reinforcement learning, there's a human designed task, but the data set is not fixed. So reinforcement learning, the agent's task, it is to learn how to collect that data in order to solve the task it's given. Okay, so we're just about transitioning in the world that you live in industry, of going from supervised learning to beginning to exploit reinforcement learning. The continual learning problem that I find super interesting at this point is the problem where neither the data set is fixed nor the task is fixed. So this is the problem that we as animals and people face, which is we learn general purpose, reusable skills and knowledge for real-world problems through experience, right? This is what a baby does as it learns from the environment, learns skills, learns knowledge. I'll break down all these pieces and make it very concrete as I go along, just a few abstract slides at the beginning. So this problem is quite different from supervised learning, is quite different from reinforcement learning. There isn't a human-defined task that we're trying to solve. It's about an agent becoming more skillful and more knowledgeable over time. So that's the continual learning problem in a nutshell. So if you, again, get another view of these three tasks, so supervised learning, the main research issues that of generalization, there are lots of other issues, of course, noisy labels, missing inputs, and so on. But it's the setting of learning from teacher-generated data. In reinforcement learning, you get two new problems. In addition to the problem of generalization, you get the problem of exploration and exploitation, but you also get the problem of delayed reward. By the way, how many of you know what reinforcement learning is? I imagine most of you, all of you. Great, excellent. So I don't have to spend time on this. It's learning from self-generated data, even though the problem is teacher-motivated. Continual learning adds a fundamentally new problem. What to learn? Because there isn't a teacher-motivated, teacher-generated task. It's autonomous learning. It's self-motivated learning. It's truly building an intelligent agent, which reinforcement learning is not about, nor is supervised learning. Really, to really build an intelligent agent means you put an agent in an environment and it gets to be intelligent in that environment in interesting and flexible ways. By the way, we've made enormous progress in terms of learning frameworks and architectures and platforms for supervised learning. We're beginning to see some of that in reinforcement learning, though certainly there is nothing like TensorFlow for reinforcement learning quite yet. Maybe you can argue OpenAI is trying to build something like that, but I don't think that's quite true either. And then, of course, we don't know how to do that for continual learning, though I have a company that's trying to do that. Okay, so now, again, a couple more abstract slides and then I'll dive into intrinsic reward. So I want to break down the continual learning problem into its pieces. So one new piece of continual learning problem is the agent, the intelligent agent that we want to build, should be able to learn new skills over time from experience. So in reinforcement learning, often we think skills in terms of what's formally called options, something I helped invent many, many years ago, but still it's probably the standard framework within reinforcement learning of what's called skills. Think of an option as learning how to open a door. It's a skill, it's a behavior, it's a policy you follow, and it succeeds or fails, but it's goal-directed, it's goals of achievement, picking up a cup, opening a door, things of that sort. Learning new knowledge. Knowledge is probably the most understudied part in the modern AI, statistical AI story, right? Which is in the reinforcement learning or the intelligent learning, in the intelligent agent context, I have a hypothesis, which is that knowledge really just means predictions. It just means option conditional predictions. If I behave in some way, what do I predict will happen? That's the abstract general form of knowledge. When I use the word knowledge, I mean that. If I open the door and look outside to the left, what will I expect to see? If I pick up this cup, how heavy will I feel it is? Or what sound would I hear if I shake it? Or if I turn it upside down, what do I expect to see? Things of that sort. That's knowledge. That's option conditional predictions. Okay, so of course, reinforcement learning is about learning skills. Supervised learning does build predictive models of the world. What's different in continual learning is I want to reuse and incorporate the skills and knowledge to learn more complex skills and knowledge in this sort of ever cascading, scalable sort of way. Of course, it brings up a whole host of issues. How do you support that knowledge and skills? How do you remember it? How do you store it? How do you avoid catastrophic forgetting, interference across tasks? All of these problems come up as you begin to think of an architecture that supports the reuse and incorporation of learned skills and knowledge over time. The thing I'm going to focus on today, I can give talks on each of these, but I'm going to focus on today is the fact that there is no extrinsic task. There is no single task necessarily, at least, that the agent is solving. Or more accurately, perhaps, there's too long a delay between extrinsic motivations and extrinsic tasks. So the agent often has time, so to speak, to learn from the environment through experience without having some extrinsic task always driving it. This is certainly true for us as people and animals and so on. So intrinsic motivation or rewards to drive experience in the absence or too long a delay in extrinsic rewards, with the view that that behavior supports the learning of skills and knowledge, because that's what then becomes useful when you have this sparse extrinsic reward. Okay, there's lots of ideas here, and I'll dive into the specific view of intrinsic reward as I finish this. And of course, all of this is in support of the agent becoming increasingly competent over time, not just in terms of knowledge and skills it has, in terms of sort of the amount of knowledge and skills it has, but also in the end, of course, in terms of how well it does at accumulating extrinsic rewards. So this connects to learning to learn, meta learning, all of these things that you've all, well, if you go to the right conferences, you'll hear about these sort of things in time. So that's the continual learning problem. I'm not going to actually address all of these pieces. I'm really primarily going to focus on intrinsic motivation. Yes, go ahead.
Just a clarifying question.
Yeah.
Is the intrinsic motivation rewards already a problem in reinforcement learning? It's not exclusive in continual learning.
Right. Yes, and in fact, many of the things that you will see me, many of the problems you will see me do are reinforcement learning problems where we learn intrinsic rewards. But the purpose of intrinsic reward in a reinforcement learning task will be to support perhaps reduce sample complexity, perhaps improve performance, online performance, in a complex reinforcement learning task. In a continual learning task, the purpose of intrinsic reward could be quite different, arguably different, in the sense that it supports the learning of the skills and knowledge, which of course, in the end, support extrinsic tasks. So it's not perhaps all that different, except perhaps in scale and complexity and richness. it is a good question. Is this problem, if you think of the problem as just sparse extrinsic reward, extremely infrequent extrinsic reward, is the problem somehow fundamentally different than reinforcement learning? I think it perhaps is in the focus on knowledge learning, which I won't spend too much time on, but I'm happy to talk more about the role of knowledge in an intelligent agent, which most in reinforcement learning stuff, tends not to spend too much time on. By the way, again, feel free to just ask any question you want. Of course, this is a very RL-centered view of AI, right? You can slice up AI in many, many different ways. This is a very reinforcement learning inspired view of artificial intelligence more broadly. Okay, so every one of you have seen this before, so I'll skip this. This is an Atari game. This is I want to spend a minute on this view because I'm going to contrast it with a different view in a minute, which is that of intrinsic reward. So now I've done with the introduction of continual learning. I'm going to now focus on intrinsic rewards, and I'm actually going to study it in reinforcement learning without really studying in continual learning. So this is a standard diagram of reinforcement learning. You have an agent interacting with an environment. There's a critic, supposedly in the environment, that provides extrinsic rewards, which defines the task for a reinforcement learning agent. So the rewards define the task. The agent's purpose is to act to maximize expected discount sum of rewards over some time horizon. Okay, so I want to contrast this with the view that comes from the optimal reward problem. So now I'm transitioning to an actual contentful talk, part of the talk. I've been quite interested in this problem of where do rewards come from. Reinforcement learning starts by saying, here's a reward function, go optimize. I'm going to step back and ask, where do rewards come from? And look at, present a survey quickly of lots of different approaches to this problem, and then dive into this thing we call optimal rewards. Okay, so in the context of reinforcement learning, why is this reward design problem interesting? It's interesting because within reinforcement learning, rewards confound two different things. Rewards are simultaneously preference definitions, and at the same time, they are parameters for the reinforcement learning problem. So, stepping back, the starting point of agent design is an agent designer. The agent designer is the one that has preferences over agent behavior. The agent doesn't have intrinsic preferences over behavior. The agent designer is the one that has preferences. So let's call this notion of preferences the objective reward function, or the extrinsic reward function. The problem is it's too sparse, it's too delayed. So the question then is, as an agent designer that's building and designing a reinforcement learning agent, what reward function should I build into the agent so that as the agent learns, it learns well, effectively, efficiently? So there are two reward functions now. The reward function of the agent designer, which defines preferences over agent behavior, and there's a reward function inside the computational agent's brain that's going to train it, which are like parameters for the agent's algorithm. In reinforcement learning, the same reward function plays both roles, but there's no principled reason why the same reward function should play both roles. We could separate these two into two different reward functions. The thing we cannot change is the objective reward function, the preferences. That's fixed. We could choose whatever reward function we want to give to the agent, and that sets up the optimal rewards problem, which I'm going to define in a minute. Okay, so I defined this difference. Rewards as preferences, which define the objective or the extrinsic reward, and rewards as parameters, which parameterize the algorithm that the agent is going to use to learn from experience. Okay, so these all seem distinct. Should they be confounded? So here is the alternative view. The alternative view is that the rewards are inside the agent, inside the organism. Contrasted with the view, the rewards are outside from the environment. The reward function truly is inside the agent. We get to design this box. this critic, so as to optimize the designer's reward functions. I'm going to make this formal in a minute. Okay, so but before I make it formal, the reward design problem is not new, right? Everybody who builds a computational agent, a robot, has to decide what reward function to give that computational agent. So this is not a new problem. So what are the different ways in which people design rewards? The one that you may have heard of, if you in the reinforcement learning field, is the problem of what's called inverse reinforcement learning. Inverse reinforcement learning designs rewards by looking at expert behavior and trying to infer the reward function the expert is optimizing and then giving that to the agent. So that's inverse reinforcement learning. I'll come back to inverse reinforcement learning. Reward shaping is another way of thinking about reward design, in which there's a bad way to think about reward shaping, which is what Andrew Ng defined, which I think is a terrible way of thinking about it. And then there's a psychologist's way of thinking about reward shaping, which is a cleaner, better way of thinking about reward shaping. You want to make the pigeon or the squirrel or the rat do a complicated sequence of things. Instead of saying, I'm going to give it a reward if it does the entire sequence, you figure out the first step it has to do, you reward it for the first step. When it learns that, then you wait until it does the first two steps, and then you reward it. That's called reward shaping. Anyway, there's a systematic way you can think of doing this. There's preference elicitation in the field of economics. There's mechanism design in economics. There are all kinds of ways of thinking about designing rewards. Okay, here's the optimal reward problem. I'm going to have two reward functions. The reward function that defines the problem, which is the preference function, which is R sub O for objective reward. That's given. I don't get to choose that. So if I'm playing the game of Go, it's to win. It's to get the score of 1 at the end, right? Or Atari games is the score I get in the Atari game. I don't get to choose that. But I can choose what reward function I give the agent. That is R sub I, internal reward function. So the agent is parameterized by the internal reward function Ri, the agent G, and any other parameters it might have, say neural net parameters, theta. If I put this agent, so the agent is now an algorithm, let's say it's doing DQN, right? If I put it in some environment ENV, then I will get a random interaction trajectory H. And I keep doing it, I'll get in principle, I'll get one infinite long trajectory H, right? The utility of that trajectory to the agent is just the sum of the internal rewards. But the utility of the agent designer is the sum of the objective rewards. So the optimal reward Ri star is the reward if I give to the agent, parameterize the agent by that reward, it optimizes the objective utility obtained by the agent designer in expectation over the environments and any stochasticity in the environments. Okay, so this is just math way of saying something very simple. The optimal reward is the reward to give a specific agent so that if it uses that reward to learn over a distribution over environments, then the expected objective utility is maximized.
One basic question. Why do we care about having intrinsic rewards? Why not I just go
with the extrinsic reward as the intrinsic reward? Exactly right. Exactly the next question. Okay, I'll give you examples in a few minutes. But the fundamental answer has to be that the agent is computationally and otherwise bounded. If the agent was unbounded in capacity, then the optimal intrinsic reward would be the objective reward. Because the objective reward, after all, you want to optimize that. If the agent was all-powerful, then that's what you should give it because it will optimize it. It's because the agent is bounded. Maybe it has finite look ahead if it's a planning agent. Maybe it has limited memory. Maybe it has limited ability to represent the world. Because of the agent's bounds, what the optimal reward does is it mitigates agent bounds. It alleviates agent bounds. And I'll show you examples of that in a few minutes. Okay, I'll actually come up with algorithms to learn these to solve the optimal reward problem. That's what I'm going, just to look ahead a little bit. Okay? So any questions about this? This is the problem this is a framework for design of optimal rewards. So if you think evolutionarily, which I have for a little while, at least in a paper that we wrote on this problem, this is the problem evolution faced, right? Evolution's reward function. Evolution is the agent designer, right? Evolution's reward function is success of the species in terms of procreation, passing on the genes. So that's the objective reward function. But that reward function, if it had built that reward function into our brains, would be no use. We can't decide how much coffee to drink in this moment based on that reward function. First of all, I'm done procreating, right? So the other thing is, in the sense that the environment distribution that I could be in is highly varied and highly stochastic, or highly basically variable. And so evolution has, in effect, solved this problem, maybe not perfectly, but has found a dopamine system. It has trained the dopamine system. It has invented a dopamine system in our brains that computes the internal rewards, that drives our emotional system, our internal reward system, that drives our behavior. Because we are bounded agents. We have limited attention span, we have limited perception, we have limited computational ability, all kinds of other kinds of limitations in our brain. Okay, so let's dive in. But it's a really important question, because the first question you should ask is, why shouldn't the optimal internal reward function be the objective reward function? It's only because we are bounded as agents, because the agent is bounded. Okay, let me give you a toy illustrative algorithm setting, which we did through in the evolutionary paper that I talked about. So it's a very contrived, simple domain. I'll get to interesting domains in next few slides. It's a domain in which the bound on the agent is its lifetime. So it's a learning agent. What I'm going to vary on an x-axis in a few minutes is how long the agent's lifetime is, how much time it has to learn to achieve reward. And this is a very simple agent environment. It's a grid world, right, in which the agent can go to the top right corner and find a worm and eat it, which is not particularly desirable extrinsically, so it gets a tiny amount of nutrition from that. Or it can pick up the worm, not eat it, go down to the fishing hole at the bottom and learn and fish, and then eat the fish. It's a very simple world. I'm learning agent, I'm doing Q learning, I'm doing lookup table Q learning. What reward function should I give the lookup table Q learning if the agent has 20 time steps to live versus 40 time steps to live versus 60 time steps to live versus 100 time steps to live? So I made up a simple bound. Lifetime. How much time to learn before life's over? Okay, so what you would expect, if I now search over possible reward functions to give, what reward function would I find? Here's what we find. If the agent's lifetime is too short, it never even gets to the fish. Then, as long as I give a small positive reward for consuming a worm as an internal reward, then it learns to at least occasionally eat the worm. Intermediate amount of lifetime is when it gets really interesting, because now it has time to at least occasionally be distracted by the fish, but doesn't really have a time to exploit learning to have fished, learning fishing. And so the reward function says eating fish is really bad. Blue is the reward for eating fish, if you like. Red is the reward for eating worm. And it says, in order not to be distracted by the fish, eating reward internally becomes extremely rewarding. In this contrived example, it learns to say eating worms is really good for you, while eating fish is really bad, so it doesn't get distracted by it. And then after a certain amount of lifetime, when it has enough time to learn to fish and exploit that, to get enough nutrition, then it reverts to saying eating worms is really bad. Don't be distracted by eating the worm. Don't eat it. just go fish. Okay, so very simple, very trivial, contrived sort of thing, and a search-based procedure for finding it. Yes, Matt.
Procedure where you have an outer loop search.
Yes, exactly right.
Weights on your
Exactly
reward functions, and then inner loop you're training an agent.
Exactly right. Exactly right. So exhaustive search to find a good reward function. I'm about to go to efficient algorithms that I can apply to Atari games and things of this sort. Yes.
So from the previous slide, I didn't realize that argmax will always have a unique.
It doesn't.
Yeah, so
It doesn't necessarily have a unique one.
right. So in this particular toy example, also you set it up so that the RI that's optimal is going to be unique, or
We found one. We didn't search for all optima. I don't think it'll matter that much whether a value is 1 or 0.9 versus, there'll be plenty of slop here.
all these optimal ones have to have this kind of shape.
Yeah, but the idea is the shape, right? If the lifetime is very small, it doesn't really matter very much as long as you don't make eating worm negative. Then at some point in the middle, it really has to say, don't eat fish. Don't be distracted by it because you don't have enough time to learn it, to exploit that. Okay. All right, so now I'm going to switch to the more interesting problem of how do we do this in real reinforcement learning and in complicated settings. Okay, so now I'm going to take a perspective that leads to a very natural algorithm. So I'm going to do two results for you. In one result, the agent is going to be a planning agent. Specifically, it's going to be a look-ahead search planning agent. More concretely, it's going to do UCT. It's going to do UCT to plan in Atari games. It's going to use a simulator of UCT, of Atari games to choose an action by doing look-ahead search via UCT. So that's the agent. But the agent is bounded. It can't do very long trajectories and it can't do very many trajectories. So it's got some bounds. And the question is, what reward function do I use with that UCT, that bounded UCT? I could use a score, which is what everyone would do, or I could invent a new reward function. The question is, how do I invent a new reward function? Okay, so that's the first paper. So the idea is really straightforward. I'm going to do model-based planning. Model-based planning is going to take whatever reward function I give and learn a policy. And that policy is going to lead to objective utility by performance in the world. So my rewards are now parameters to my planning UCT-based agent to create a behavior that gives me objective utility. So now I want to optimize this reward function. All I'm going to do is I'm going to backprop, if you like, through the objective utility, through the planning procedure, and update my reward function. So the only thing I'm going to learn from episode to episode is how to change the reward function. The agent algorithm is fixed. It does UCT with my learned reward function to behave in the world. And I'm going to try and optimize that reward function so that limited bounded UCT does better than it would with this objective score as a reward function. Okay, so that's the algorithmic idea. Yes?
No, the earlier thing was an expectation. It was an argmax over two expectations,
Right.
and you instead right now only have a Monte Carlo sample of
That's right.
one of those.
In this case, I have a single task, a single game. So I don't have a distribution over games.
Right?
The only expectation is over trajectories.
Right.
So I am going to optimize over trajectories, just like any. So what does this remind you of? This reminds you of policy gradient methods. The difference is in policy gradient methods, the parameters are neural net weights. Here, the parameters are the reward function. UCT converts a reward function into behavior, which has an objective utility, and I want to optimize that objective utility by doing the gradient with respect to the reward as parameters of policy gradient.
So, what is the objective utility in this case?
Score. I'm just playing an Atari game. It's the score of the game.
So, that is a extrinsic.
That's the extrinsic utility. It's the agent designer's utility. Okay? So I'm not going to go through the slide, but basically this shows you how you do backprop through a planning procedure. It turns out, well, let me just go through it briefly. I want to compute the theta are the parameters of the reward function. So if the reward function is a neural net, theta are the weights of the neural net that define the reward function. I'll show you slides in a visual of that in a minute. So I want to compute the derivative of the expected objective utility, R sub O, of the actual trajectory with respect to theta, given the agent uses theta as the parameters. So I'm going to break it down into two pieces. The first piece is, which is what policy gradient always does, it takes the gradient of the objective utility with respect to the policy action choices. And then I take the derivative of the policy with respect to the reward network weights. And it turns out that you can compute remember the way the reward impacts the policy is through this UCT trajectory, set of trajectories. So I have to sort of essentially do a gradient through the trajectories, which sets up a recursion, and I can do a recursive procedure. Just like backing up values of the UCT trajectories, I can back up these gradients up the UCT. So it's like just double the computation, basically. I do twice as much computation of the tree, and I can compute the gradients. Okay, so I don't want to show you this, but basically, all right, I must show you a video or two. Here is UCT with these learned reward functions playing, but this is not the interesting thing. So here's the interesting thing. So this is the computation UCT does. It basically computes the average over a set of trajectories of the discounted reward along those trajectories. This is the objective reward. I'm going to use a CNN whose parameters I'm going to learn that's going to take the images. Notice this is not learning. This is UCT. This is from the simulator, using this Atari simulator. This is the thing I'm going to learn. It's going to output a additive internal reward, which is going to be added to the extrinsic reward. So the output of the CNN is going to give me a bonus, a reward, intrinsic reward bonus that gets added to the objective reward, which is then going to be converted via a softmax function into a policy, which is going to give me a utility, and then I backwards go through all this process, and then I can update my value function. Okay, so when I do that, we tried, 25 Atari games. I'm going to look at a ratio of performance. If it's, and this gray line means 1. So anything to the right of it means we got an improvement in performance. About here is 10, a ratio of 10. About here is a ratio of 100. Anything to the left of the gray line means we did worse. So in most of the games, okay, what's the setting? The setting is I have a fixed UCT. I didn't tell you how many trajectories, how many trajectories in what depth, or whatever it was fixed. And I compare the performance with using the score as the reward function versus the learned after learning. I'm not showing you learning curves because I've used repeated UCT training and backprop through it to learn a reward function. After I've learned the reward function, I'm showing you performance. Okay? Okay, but there's a little bit of cheating here because, of course, I'm doing twice as much computation, if you like, with the internal reward function because I have to run through the CNN. Well, it's not twice as much. It's just more computation, but I have to run a forward pass through the CNN for every expansion in UCT. So that can be expensive. So this is not fair because I can do a deeper, wider UCT with that same amount of computation time. So to make an apples-to-apples comparison, we did a deeper, wider UCT with the score as the reward function compared to this shallower, narrower UCT with the learned reward function so that the amount of computation per action is the same. And then the orange curves are the new curves, are the new ratios. So we lose in a couple of games, more games, but we still win many games. Okay. All right. So that's the first piece of the talk. We did planner, UCT planner as the reward as the agent design. The agent is bounded. As the agent is bounded. We learned through experience how to set the reward function so that same shallow, narrow UCT does as well as a deeper, wider UCT. Yes.
Have you tried just swapping out UCT with other RL algorithms to see if the reward you learn is robust?
No, but we have done other papers in which we have tried other. So This is a sort of a well-founded algorithm, right? It's just basically gradient descent, right? Any procedure that's differentiable, you can use this with. So what it requires is an agent that has a differentiable procedure to convert a reward function into behavior. Then we can design rewards this way. And I'm about to show you. For the longest time, I thought we could only do this with planning agents, because at least the planning agent is fixed. Sorry, go ahead. Finish your question.
So that's not actually my question. My
Right.
question is that you learn the reward function.
How robust is it?
Yeah, you learn it using one algorithm, and then you test it on another algorithm to see if it's actually.
Did not do that. It's a very interesting experiment to do. Did not do it. Though I'm actually doing something that comes close to that, but it's a very good experiment to do. Did not do.
Curious if you had any intuitions on what the learned intrinsic reward functions were providing.
Yeah. For a while, I was worried that what they were learning is a bias over actions independent of state. That is, they learn. For a while, I was worried that they just say, you know what, it's better to fire. Slight bias towards firing, and that could be the difference, which would not be a very interesting reward function to learn because it's not a function. It's just a priori bias. So for a while, I was worried that that's all that was going on. So we were able to do some analysis to show that's not what's going on. Okay, so that's the good news. The bad news is it's not clear how to intuitively capture, or we didn't spend enough time trying to intuitively capture what it is that those reward functions. I think both of these questions are super interesting. It would be really useful. Let's wait for the next snippet of talk, which is an extension to this, and then let's come back to this question, because I'm actually very interested in this direction. Sorry, you had your hand up.
So, I'm just confused. So, is the one that's backdropping through UCT, does it have access to more interactions to the Atari score environment than the orange box?
Okay, remember what let me remind you again what the comparison is. The comparison is an agent that plans with the objective reward as the score as a reward. That agent doesn't learn anything. It just, right from the start point, right, it's going to produce a score. That's not a learning agent. It's a planning agent. It's going to do fixed UCT. So I'm comparing that agent with a learned reward function, which I learned through experience. I'm not telling you how much experience. Lots of experience. But that's not the point here. The point here is to show that we can actually learn. Next experiment is going to be more interesting. I'm going to do a learning agent. Okay? All right. So let's just go to the next experiment. So this is on archive. Just put on archive 2 weeks ago. It's under review for a conference. Hopefully none of you are reviewing it. So for the longest time I thought the planning agent is a fixed agent. It doesn't learn. So I can just learn the reward function. The reward thing is the only thing I learn. Suppose I have a learning agent. Now I have this really interesting thing where I'm learning the reward function to use by a learning agent. So that's like two things learning, and that's complicated. That is, the learning agent's reward function is now also changing. The learning agent is changing. How am I going to do this in a sensible way? So I have this new student, Jie-Yu Zhang, who just came on board and said, I know how to do it. And he did it, basically. And it turns out it's actually a very nice, it's a first-year student. And he has a very nice idea. Actually, in hindsight, straightforward idea, but actually works really well. So now we're going to do a learning agent. We're going to do, in particular, actor critic-like agents. So policy gradient learners. So inside the agent are two boxes. A policy gradient learner will use A2C in Atari, and we'll use PPO for Mujoko domains. I'll show you results in 2 domains. And the intrinsic reward box is going to output an intrinsic reward as a function of state. The policy learner is going to learn by the weighted sum of the extrinsic reward and the intrinsic reward. The intrinsic reward box is going to learn just from the extrinsic reward. So the intrinsic reward is going to learn to optimize the extrinsic reward in such a way, but the behavior is generated by the policy box, the policy gradient learner. So we have to do now proper, correct gradient procedures to do this really non-stationary process. The thing you have to ask is, conceptually you have to ask is, how do I change the reward function so that the learner, as it learns with that reward function, will improve my objective reward utility? You have to solve that gradient computation question. It turns out it's actually a very straightforward, I had thought this was not going to work, but actually a pretty straightforward way of doing it. So I'm actually not going to say more about the algorithm. You can find this paper on arXiv. It's a very straightforward algorithm. I'm just going to show you some results. So these are results where the baseline, the policy gradient agent is A to C. So we're using a state-of-the-art, actually OpenAI's implementation of A to C. There are about, how many games here? 4 times 13 games here. The red curve, so x-axis is the amount of experience. So now I'm comparing apples to apples by just controlling for the amount of experience on the x-axis. The y-axis is the Atari game score. And you're seeing multiple runs. The dark lines are the average of, I think, when I drew this graph, there were 5 runs or 3 runs, I can't remember. But now it's so expensive, we're trying to do more runs. And basically the bottom line is, at this point it's very hard to beat the baselines in Atari or Mojoko because they're so highly tuned to those domains. So you don't get massive wins anymore. But just by adapting the internal reward, during learning, the agent ends up doing better in most of these games. Not all of them, but most of them. Okay, so again, just to show you what the procedure is, right? We have an A to C learner, which is this box. We have an intrinsic reward box, which is another CNN-based network, right? Just on Atari games. In fact, it's actually the same architecture. Literally the same architecture. The output of the actor here is actions. The output of the actor here is a reward function, is the scalar reward. Literally the same architecture duplicated. We're just doing the gradients through this, so it learns a reward function. I haven't done any of the interesting follow-up things. What does it learn in terms of reward yet? I want to show you one more slide, and then I'll come back to this. We also did this in the Mojoko domains. The columns correspond to the 5 different domains we tried it on. Again, red is our color, blue is the baseline agent's color, in which case this is PPO. We're using, PPO is very hard to beat in these domains. PPO, and we're doing a learned intrinsic reward with PPO. The rows correspond to delay in reward. So it turns out that in Mojoko domains, the reward is not sparse at all because they have designed really frequent rewards. So the way we're making the task harder is we're accumulating reward over a certain number of steps before giving it, the extrinsic reward. So there's 10 times step accumulation before giving it, 20 and 40. So in some sense, the task gets harder. So all the performance gets a little worse. But for the most part, other than, Ant, we certainly don't win, except we don't really win. But in many of the other domains, we are, and we're getting more results as we speak. We get a win even in this sort of setting. Okay, some people had their hands up. Go for it.
Yeah, you in one slide you mentioned so there are 2 models and they had the same architecture.
Yes. Mostly for convenience, but we didn't do a search.
I have a general question about like whether to use duplicate like 2 different models with the same architecture versus one joint model.
We've tried some of that. To the extent that you think the hidden representations are shared between the reward function, the good reward function, and a good, policy learner, you can think of it as an auxiliary task that actually would help the training of these things. My memory is that, you tried this, it didn't make a difference or didn't work. One of those 2 things happened. I forget which one at this point.
So I'm facing a similar problem. On the one hand, they seem to share some representation, some lower level of representation. Yes. But on the other hand, like if we use a single model, how we compose the joint loss function.
Right.
How do we combine?
But that's not a new problem. We know how to do auxiliary tasks. And I don't know exactly which context you're facing this, but the brutal reality is people just do a hyperparameter search over how to mix the loss functions so that they get some good performance. Or then if it doesn't work, then they separate it. And so there's a little bit of design of architectures that plays a role here. I think he did the most sort of the first thing, which was just had the same architecture and had some shared initial layers, but then the last few layers were different, and that just worked. Doesn't mean that something else wouldn't work better. Yes.
So I mean, policy gradient, I always worry about, am I just like converging to some local optimum in
Yes.
policy space?
Yes.
I'm curious if this way of parameterizing these policies with these two boxes, did you, before trying TPO and this, did you actually convince yourself that this parameterization wasn't more vulnerable or less vulnerable to such local convergence issues? Like when you first said the idea, I had the same anxiety as you, right? Like, will these two things actually converge to a very terrible local optimum?
Yes, they didn't. So I don't have any theory that says this is going to converge. So one theoretical, we know policy gradient, at least in the lookup table setting with two-scale learning, two-scale step sizes for the actor and critic, you can, at least in that asymptotic sense, talk about convergence. I don't know if in the lookup, so what we have not done is ask, okay, fine, functional approximation is hard to analyze. Let's analyze this in the lookup table, asymptotic setting. Can we say something about this? We haven't done that yet. This is just very, very, very recent work. Matthew, you had a question earlier. No? Okay. Yes.
Another question is, so when I view it from the model-based point of view, so you add the intrinsic function model on top of model-free policy.
This is still model-free in the sense that...
Yeah, so this is model-free, but my question is, have you tried on model-based?
So the first part of the talk...
Because the model-based will have some... It learns from more data, the transition data, which may reduce the gain of
So
regularizer.
we have not tried learning reward functions for a model-based learning agent, except the planning agent is a model-based learning agent, but the model is given a priori rather than being learned. So model-based reinforcement learning, like story, we have not tried yet. Okay, I'm gonna skip this part of the talk because I think I will go to things that I suspect you'll find more interesting. So let me go to. I'm going to skip this bit about inverse reinforcement learning. This is the theory part of the talk from one of my students, Nan Jiang, whom I think some of you know of. Instead, I'm going to talk about something else that's not even published that I'm actually quite excited by, which I'm calling on many goals reinforcement learning. It's going to be brief. I'm going to promise to finish by 4:30 on this one. So this will be on archive by the end of May. We're still doing this. You don't run out and write a paper on this. Sorry, just joking, just joking. Okay, so here's the idea. In 1993, I was scooped by a colleague of mine on a beautiful idea, Leslie Kelbling. I was a grad student. I go to this workshop, and Leslie Kelbling presents this work that had been thinking of the last month, but I hadn't done it, and she had done it. And it's beautiful work. This is the idea of what's called all goals updating. So it's particularly pleasurable to come back to it and actually use it because I didn't get a chance to benefit from it all those years ago. So the idea is very straightforward. She did it in lookup tables because this is 1993. We didn't have TensorFlow and all that kind of fun stuff. So it's a very simple idea. Q-learning is off policy. How many of you know the distinction between off policy and on policy? Almost all of you. Okay. Basically, let me explain off policy in this equation in a minute. So there was two ideas in this beautiful work by Leslie Kelbling. One is not her idea, but Q-learning is off policy, but she took that and did the following. She put an agent in an environment, a small grid world, and had it learn a separate Q-value function for each goal. And that was not the interesting part. The interesting part is you could update each goal's Q-value function from every transition in the world. So suppose you see a transition that the agent took action A in state S and experienced state S prime. Then for all goals, for all possible states you want to go to, where you keep a separate Q-value function indexed by the goal G, you can do the following update. You can say the new Q-value is 1 minus alpha times old Q-value for that goal plus alpha times the reward for that goal from this transition plus gamma max Q-value the next time step. Q-learning is off policy. You can do this and basically you can get unsupervised mastery over the world in a provable sort of way in a lookup table setting. So we wanted to do this in today's world. And of course, you can do all goals when you have a finite small number of goals. In today's world, we can have infinite goals, so we'll do many goals as opposed to all goals. Okay, so here's the idea. I'm going to present to you three slides with three different, or a few slides with three different little vignettes of ideas. Here's the first one. We took a simple domain in which there's a wall and a door. There are two switches in each room which can open the door. The door shuts after a while after you open it. There is sort of sand which is hard to move over. There's a block that can be pushed by the robot, which is a circle. It's a very trivial world. The world will be given as input visually, so you'll get a visual view of the world. It's a 2D grid world. But there's combinatorics here, right? The block can be in any different of these positions. The door could be open or closed. The robot could be in any position. So the number of states in the world that you could try and achieve is whatever it is, some thousands. So we're going to use a neural net, which looks like this. It's going to have a number of layers, which is going to give the state, the visual state, as current state as input. And it's going to be given a goal state, a visual goal state as input, and is going to learn a goal indexed, if you like, a Q-value function for state actions and goals. You can think of it as universal value function, if you like, however you want to think about this, right? And we can use all goals updating, many goals updating, any kind of algorithm like that, and there are details to the algorithm that I won't spend time on. And basically, this x-axis, we just explored two different methods of how to generate the experience to train all goals, to train this neural net. And every so often, we stop and we ask it to do every possible goal, and we ask how many of those goals it succeeds on. So this is the fraction of goals it's succeeding on, and basically over time it gets to after this many steps into training. This is, by the way, 10 to the 7. It gets increased mastery over this world. So it's in an unsupervised way, with no extrinsic tasks, just by generating experience. It's learning to be able to do everything that's possible to do in principle in this environment. What I'm not showing you yet, because we're generating the graph right now, is if we didn't do multi-update, if we just updated online and the goal we're actually following, what would that curve look like? And basically, I expect it to look something like this. We're just generating this.
The requirement is that goal should at least be depicted as an image.
In this case, but it's not really necessary, right? That's how we're doing it. We don't know in advance what goals are achievable. So what we do is every time we encounter an image, we put it into our goal set, a new image. So our goal set keeps expanding, and we're learning. Because remember, it'll take a long time for it to actually first learn to open the door by chance, and then learn to move this block around. It's not going to experience many of the goal states. So we don't give it all the goal states in advance. We let it just experience. For this thing, we measure it in all possible states we know it can achieve. But we don't, during training, it doesn't know all the goal states in advance. It just says, every state that I've ever achieved, I know I can achieve. So I'm going to put it in my goal box. Yes.
Have you compared against hindsight experience replay?
Yeah. Hindsight experience replay is a variation of this, and it's actually, first of all, it's not trying to do mastery. Hindsight replay is about trying to do one task, but updating on many tasks to support that task. So first of all, the objective is different. They're not trying to do mastery, so it doesn't make sense for them to achieve mastery. They're not trying to do mastery, right? So they won't achieve mastery because they can't even do this problem because they have a task to do. Nevertheless, that idea is not inconsistent with this idea. That is, we could use similar ideas for how to take things from memory replay. What I'm not telling you is how we are choosing what to update. We can combine this idea with hindsight replay to choose what to update. So in some sense, they are orthogonal ideas. This is about achieving mastery. It's about updating many goals. Hindsight replay is one way of choosing which goals to update. So we can certainly do that as part of this. Okay, so that was that, mastery. I'm going to do very quick things and I'll be done. The next thing we did is, well, we said, suppose there is an extrinsic task. Can we still use this? How would we use this? So the first thing we did is, we said, suppose there was a pre-training phase where the agent, without any extrinsic task, just gets to explore in this environment and learn about lots of things. And then, subsequently, it faces the task it's going to be examined on, and then it has to see how well it does in that task. So now we have a slightly different architecture. Again, you have a goal network and a mapping from, we're going to switch now, we were doing Q-learning and that sort of thing, we're going to switch to actor critic because you want to do much bigger tasks where actor critic tends to work better. Okay, so we're going to do a pre-training phase in which we are going to do the bottom, we're going to train sort of this path without that path, okay? And we're going to learn good internal representations that solve many, many tasks. And then after that, we're going to give it the task we actually care about and see how well whether it benefits or not. So here's the results. And this is a fair comparison. Well, I'll tell you about that in a minute. So the x-axis, the black curves are A to C, and the blue curves are A to C with pre-training. So it's doesn't beat in every single task. We're still getting more results on this, but it beats it in many, many tasks. So these are, how many? 9 or 10? I can't remember. Yeah, 10 Atari games in which, again, A to C is not that easy to beat. And our pre-training procedure outperforms in most games except boxing. Is that right? Boxing and maybe Miss Pac-Man. Okay, so this is pre-training where we use 1 million steps for pre-training and we give 9 more million steps to our blue curve, we give 10 million steps to the black curve. We're comparing that way. Yes?
Well, what were the goals that you were in these? Were other
The goals were simple. No. It's the same game. The goals are to achieve any image that you can achieve.
So it'll just learn to go to different places.
Yeah. Just achieving particular. We pick possible goals from things that it actually did, so we know they're achievable. Okay? Then we did a third thing. So you have a head up, yes.
But the extrinsic reward still stays the same, so it's just the image. It's
This
not
has
like
nothing to
your
do with the
time.
intrinsic reward story.
Okay.
Sorry, just to be clear. This is a separate piece of work, right? Yeah, this is only extrinsic rewards. But the extrinsic rewards are defined by the goals. So the goal is to reach a certain image. We give a goal when he reaches that image. Okay. Then we said, okay, well, suppose we didn't want to do pre-training. Can we exploit this idea in a different way yet? So now we are going to do the same architecture, except we're going to use this many goals updating as auxiliary tasks. So you've all maybe seen this work where people show that you can use auxiliary tasks like reward prediction that helps learn representations suitable that accelerate the performance on a main task, or pixel control or other auxiliary tasks like that. So the idea here is to use the same kind of all many goals updating as auxiliary tasks instead of pixel control, instead of reward prediction. And this is too busy a graph. You can guess which color is ours. Green. Okay, good. And we're going to compare, let me show you a different view of these. So these are 49 or 50, I forget, Atari games. And this is gain by doing the auxiliary tasks based on all goals, percentage gain or percentage loss in performance over a certain time, at the end of that time period, and over A to C baseline. So A to C baseline doesn't use auxiliary tasks. We use the additional auxiliary tasks. This is the graph when we compare many goals auxiliary tasks versus pixel control as auxiliary tasks. Turns out pixel control doesn't really work. So pixel control is where the auxiliary task is you pick a pixel and you say, I want to learn to optimize the discounted sum of that pixel. And you do it for all the pixels. That's the pixel control task. And here's one where the reward prediction was the auxiliary task. And we get better performance in each of these instances, yes.
Do you have any insights on what in the game makes this performance different?
It's the same thing we talked about in the previous discussion, right? Is the idea of auxiliary tasks, right? Auxiliary tasks say, the reason why auxiliary tasks can help learning good representations because you're forcing the representation to do many different things in the same environment. People have proposed specific auxiliary tasks, like let's control pixels, or let's predict reward. This is a more general purpose idea in some sense. We're just saying, imagine achieving whatever you can achieve in that environment. Of course, that could be too many things. So you still have some layer of sort of saying what subset of that you might want to predict, might want to learn. But it's the idea of I'm showing you 3 different ways of using learning lots of things. The first one was where that is the task itself, mastery. I want to learn lots of things. Second one was, let me use lots of things in an unsupervised phase to learn good representations to support the task I truly care about, playing that game. The third one was, let me use learning lots of things as auxiliary tasks to support the representation learning of the one that I'm showing on the slide right now. Okay? Okay, I can go on and on, but I won't. It's 4:38, so I'll stop. And just leave it with this overall summary.
We have a few more minutes up to you, but how about we formally conclude and we can continue discussion?
People can stay and we can talk.